Let's take a look at some notes here, everyone. In fact, the statement of the form for every x in domain U, if Px, then Qx can always be written in the form of for every x in domain D, Qx. What are we basically doing? We're narrowing U to be the domain D, which consists of all values of variable x that makes Px, your predicate, a true values. So conversely, a statement of the form for every x in domain D, Qx can be also written as for every x, if x is in domain D, then Qx. Let me highlight this one for you. For every x in domain D, Qx, meaning that for every x, if x is in domain D, then Qx is true. That's the whole goal. Another note for you. Let Px and Qx be predicates and suppose that they have a common domain like D. The notation Px then Qx means that every element in the true set of Px is in the true set of Qx. So that's the meaning of that. For every x in the common domain D, Px, then Qx, meaning that every element in the true set of Px lands in the true set of Qx. The notation Px if and only if Qx means that Px and Qx have identical truth sets, or equivalently, for every x, Px if and only if Qx. Very well. Let's go over one example so we feel a little bit more comfortable about what's happening here. Suppose Qn be the statement n is a factor of 8, Rn saying that n is a factor of 4, and Sn be the predicate saying that n is less than 5 and n is not 3. Suppose that the domain of n is positive integers. We're going to use implication and biconditional symbols to indicate the relationship between Qn, Rn, and Sn. So first of all, what's the truth set for your Qn? Let's use different colors. For example, for Qn, the truth set is, since they are all in positive integers and factors of 8 are 1, 2, 4, and 8. And then let us move on to Rn. For the truth set of Rn, these are all factors of 4, 1, 2, and 4. So obviously you can see that the truth set for Rn is a subset of truth set for Qn. And finally, for Sn, the truth set for Sn, all positive integers that are less than 5, 1, 2, 3, 4, and n is not 3, so we get 1, 2, and 4. So obviously you can see that Sn is a subset of Qn, and at the same time Rn is a subset of Qn, and obviously Sn and Rn are equivalent to each other. Sn is equivalent to Rn. They're basically the same. And we can write it basically this way. We're going to say that, hey, Sn, then let me use the same color. Sn implies Qn, and also Rn implies Qn. And Sn and Rn are equivalent. Sn if and only if Rn more practice for you, everyone. We want to find counterexamples to show that the statements are basically false. So let's take a look at the very first statement, our very first statement, saying that for every real number, if you take any real number, it doesn't matter who's choosing this real number, x is more than 1 over x. Can we find a counterexample? Well, we have many possibilities for the counterexample here, right? Each one of you can come up with a counterexample here. First of all, this is a universal statement. This universal statement is true if and only if it's true for every single value in the domain. For every single value in the domain. So if you can find one value that doesn't fit into this statement inequality, then it means that you found a counterexample. But obviously, if you plug in 1, 1 is not more than 1. 1 is more than or equal to 1. So each one of you can come up with a counterexample here. This universal statement is false. Take x to be 1, then 1 is not more than 1, correct? So we found a counterexample. Again, you can come up with other counterexamples. You might say, hey, I want to take another counterexample, like what? Like a half. Well, a half is not more than 1 divided by a half or 2. You can find more counterexamples. Another example for you. Okay. B and C. B says for every A in Z, for any integer, A minus 1 divided by A is not an integer, right? This is again a universal statement. It is true if and only if it's true for every single value in the domain. If you can find one value that make this statement to be false, you found a counterexample. So the statement is going to be false all the time. For example, you can take A to be 1 or any other value that fits into this statement and make the statement to be a false statement. So it says for if I take A to be any random integer, A minus 1 divided by A is not an integer. But if I take A to be 1, we find a counterexample. This universal statement is false. Why is that? Take A to be 1, then 1 minus 1 divided 1 is 0, which is an integer. For example, you might be interested in using A to be like negative 1. Negative 1 minus 1 divided by -1 is -2 divided by -1, which is 2. It's another integer. So we found counterexample. C says, for any positive integers like m and n, m times n is more than or equals to m plus n. Well, take a look. This is another universal statement, which is false. This universal statement is false. Why is that? Take m to be equal to n to be 1. 1 times 1 is 1, which is more than or equals to 1 plus 1, which is 2. So we found a counterexample. This universal statement is false as well. Let's take a look at another one. Here we go. D says for any real numbers like x and y, square root of x plus y is always equal to square root of x plus square root of y. This statement in general is false. D. Can move this a little bit up so you can fit everything here. D. This universal statement is also false. Take x to be equal to y to be just 1. Then square root of 2 is not square root of 1 plus square root of 1 or 2, right? Very well. Let's move on to another example. Let R be the domain of predicate variable x. So you have a predicate like p of x and you have a variable like x, and the domain is R, all real values. Which of the following are true and which ones are false? So let's take a look at these statements. The very first one says, if x is more than 2, then x is more than 1. Well, this is a true statement. This universal statement is true all the time. Remember that implication means that we have a universal statement. Is true all the time. So again, P then Q is a universal statement. Let's take a look at another one. Here we have x is more than 2, then x squared is more than 4. Very well. In this case, it says for any x that is more than 2, x squared is more than 4, right? I can visualize this. I showed you before in one of the examples that using algebra, you can basically see that this is a true statement. True all the time. Remember that we had a quadratic function, and then for that quadratic function, we saw that when x is more than 2, your function x squared minus 4 is positive. Also on the left hand side, if x is less than -2, your x squared minus 4 is also positive. So B is true all the time. Let's take a look at another one. Here I have C, which says x squared is more than 4. Then it implies that x is more than 2. Well, let's go back to the algebra, to what we did before. This is a false statement. right? So C is false. We can check the graph or use numerical values. You might say, hey, let's take x to be, for example, -3. Like x is -3 and -3 to power 2 is more than 4. Obviously, 9 is more than 4. But it doesn't imply that x is more than 3, right? So this is a false statement. Let's take a look at the last one. The last one says x squared is more than 4 if and only if absolute value of x is more than 2. This is a true statement. This is basically the definition of absolute value function. So here we say that absolute value of x is more than 2. What's the meaning of that? It means that x is more than 2 or x is less than -2. Exactly the same as what we did for our graph here, right? Now take a look at the y values. X squared minus 4 is saying that this portion of the inequality x squared minus 4 is positive, which is exactly what we showed from the graph in quadratic form. So remember that in general, if you have absolute value of x more than a, it means that x is more than a or x is less than -a. This is what we learned from algebra. Very well, let us move on to next example for you. Here we have the domain to be R, and we want to check to see which statement is true, which statement is false. It says A is positive and B is positive, then their multiplication must be positive as well. So this is a true statement. The product of any two positive values is positive all the time. So this is a true statement. The universal statement is true. Let's take a look at another example. Here we have, if A is less than 0 and B is less than 0, then AB is negative. Very well, this is a false statement. We can find a counterexample. Let's say A is -1, B is -1, A times B is 1, which is positive. So this universal statement is false. Let's take a look at another one. It says if AB is equal to 0, then A is 0 or B is equal to 0. It says for all numbers like A and B, if their multiplication is 0, then one of them is at least 0. This statement is true all the time. So this is my A, my B, and C is true. You have a universal statement which is true. This one says if A is less than B and C is less than D, AC is less than BD. Remember that your domain is R. The domain here is very important. The domain is R. It's not positive R values. So it means that you need to take into account the negative values as well. This statement is going to be false. Why is that? For example, if I take A to be -2 and B 1, well, obviously -2 is less than 1. Take C to be like -3, which is less than, like, let's take this one to be 1 again. It doesn't matter. Then AC is +6, which is not less than 1 times 1, which is 1. This is a false statement. So D, we can find a counterexample.